this on the computer. So yesterday we have discussed and explained about the case where we have only independent sources inside the circuit. Yeah, we have explained the proof for this Thevenin and Norton's theorem, and then we give some examples on the application of Thevenin and Norton and how to find the open circuit voltage, which will become the Thevenin equivalent voltage source, as well as the independent current source for the Norton equivalent circuit. And we have discussed some examples on that, solving by source transformation, and then solving also by Thevenin equivalent circuit. Okay, and then after that, so sorry, we just go at a glance of what we had learned yesterday on different steps to compute parameter inside the circuit using either source transformation or using then Thevenin equivalent circuit, yeah, or Norton equivalent circuit. And then we had discussed on the general procedure of determining the Thevenin equivalent, either the open circuit voltage, the short circuit current, and then the Thevenin equivalent resistance. And then we did some examples on this, especially when there are only independent sources inside the circuit, either independent voltage source or independent current source. Okay. So this is from yesterday example when we have only independent sources inside the circuit. So I hope it is quite clear for everyone, each of you, how to be able, when you are given a circuit, how can you determine the equivalent Thevenin equivalent circuit or Norton equivalent circuit. The problem, I'm not saying the problem, but maybe it's a matter of choice. At which part of the circuit you would like to separate or make partition, yeah? to make partition inside the circuit. If you want to have later a straightforward calculation of the output across or voltage output or current output across certain load, like resistor here, what you can do is you can immediately cut at the end terminals of that loading, yeah, component. Alternatively, but usually then it will create a little bit confusion or a bit complexity in redrawing the remaining part A, the left part of the circuit, in order that you can find the Thevenin equivalent resistance or the open circuit voltage. Alternatively, you can solve one by one from the left part. So you develop several Thevenin equivalent circuits until you obtain the closest general equivalent circuit close to the part of the circuit that you want to solve the voltage or current. Okay, so these are some of the examples that we had discussed and yesterday. Okay, so there is usually there are several options, yeah, to solve a problem. So not necessarily you have to do this or that. You know, even using one single theorem, Thevenin or Norton, there are also different options where you can make partition inside the circuit. And part of Thevenin and Norton, you can also use superposition and then source transformation, and then also linearity theorem, etc. So in any problem, in any quiz or exam, then you have to follow the instruction, which method that the problem maker would like to use, yeah, for you to use, which method that they would like you to use to solve the problem in that particular circuit. Okay, so this is also what we had discussed also yesterday, simplifying the circuit and then obtaining the resulting equivalent circuit. Then also What if we want to use this? One circuit like this can be solved using either Norton theorem or Thevenin theorem. If you use Norton theorem, then what you obtain is an equivalent current source with a parallel resistor, parallel equivalent Norton resistor. If you use Thevenin theorems, then what you will get is equivalent independent voltage source in the Thevenin voltage and the Thevenin resistance. Okay, this is also we had discussed yesterday. Using circuit with independent sources only. These are some sample problem that we had discussed yesterday. Okay, so now the current discussion, today's discussion, we will try to use circuit which has only the dependent sources. Okay, so for example, here we have a dependent voltage source, current controlled voltage source. The voltage value is dependent on the current Ix flowing through R2. So here, using first here voltage minus AIX, and using loop analysis here. Inside this one, we obtain negative AIX, which is a voltage. Then R1 plus R2 times IX equals 0. So this is using loop analysis. Then in this loop, we obtain negative AIX. So this is a simplification of this. Negative A times plus R1 plus R2 times IX equals 0. Now, if negative A plus R1 plus R2 is not equal to 0, it means that Ix is equal to 0, because the value of resistance here could not be 0. If it is 0, then it means it's short circuited. If the value of A is also not 0, cannot be 0. So a circuit with only dependent sources cannot self-start. Actually, that statement has to be qualified a bit. What if now A equals to R1 plus R2? So here, if this value is not 0, it means Ix will be 0, which is not possible. So that's why it cannot self-start. So it means here, this could be 0. It means A would be equals to R1 plus R2. So for any properly designed circuit with only dependent sources, the open circuit will be 0, and the short circuit will also be 0 in this case. So this one, we will obtain that the Thevenin, since VOC equals to 0, right? So the Thevenin equivalent source will be 0, which means it is short circuited. The left part. It only contains Thevenin resistance. So this is a big simplification. However, we need a special approach for the computation of the Thevenin equivalent resistance. Because it cannot self-start, then we need to probe using an external source. So usually we make some assumption using an external source. The source can be either a voltage source or a current source, and its value can be chosen arbitrarily. Which one to choose is only determined by the simplicity of the resulting circuit. Say here. So for example, if we choose a voltage probe, then we connect an independent voltage source having a value of 1 volt, to the terminal A, B. Okay. So using the previous assumption, it means then the Thevenin voltage source, the Thevenin equivalent voltage source will be 0, right? Short circuited. So a current will flow from this voltage probe into the circuit. We must now compute that current IP supplied by this probe source, the Vp. Okay. Then the Thevenin resistance. Okay. So when it is connected, and will be Vp divided by IP, the current IP flowing from that voltage probe. So in this case, if there is no R2 here, in the upper circuit, then IP will be equals to IX plus the current here. The current flowing here is VP here minus this voltage here, which is AIX divided by R1. Yeah, from nodal analysis using Kirchhoff current law. Okay, so from here then we obtain after simplifying, this IX will be here equals to VP divided by R2, yeah, because the VP is this point, yeah. Let me draw. So VP is this node, yeah, this is connected node. So IX equals to VP divided by R2. So we can replace this into this formula, and then from there we will obtain IP equals to 1 over R2 plus 1 over R1 negative A divided by R1 R2 times VP. Okay, so substituting this inside this equation with VP divided by R2. So from here, then Thevenin resistance will be obtained as VP divided by AP, which is basically this VP, this value, right? This value is the Thevenin resistance. So Thevenin resistance is calculated when we short-circuited the voltage source. The value chosen for the probe voltage is irrelevant, yeah, this VP. Oftentimes we simply set it to 1. Usually we just set it to 1 volt. This is for when the circuit only contain dependent sources. So what about if now we choose a current source probe? We can also choose current source probe. Okay, so instead of voltage probe, we put current probe. So usually we choose 1 ampere flowing into the circuit. Okay, then we have an IP here, also here. This is after substituting into the Thevenin equivalent circuit. So now we must compute the node voltage VP here. So the Thevenin resistance according to this will be equals to VP divided by IP. So what is VP now? So using KCL at this node, VP divided by R2 plus VP negative AIX divided by R1 negative IP, because this is entering into the node, okay, equals to 0. And here IX equals to the VP divided by R2, so it's basically similar like this previous slide. Then we can substitute this into this part, okay, so 1 over R2 plus 1 over R1 negative A divided by R1 R2, okay, times VP equals to IP, this current source. So usually we choose IP to be 1 ampere, 1 milliampere, okay. So that then 1 ampere we can after obtaining VP we can calculate the Thevenin resistance. So let's try with some examples. Find the Thevenin equivalence of the circuit. This contains only one single dependent voltage source, which is dependent on the value of the voltage across this 1 kilo ohm voltage. What do we use current probe or voltage probe? If we use voltage probe, there is only one node not connected through the source, which is this node. Okay, yeah, this node is connected to the source. This one is connected to this one, but this one V1 is not known. So let's say we connected into a single a 1 volt voltage probe. And so this will be VP. Yeah, this whole node will be VP. Then the Thevenin resistance of the whole left part of the circuit equals to VP divided by IP. So IP here is the current flowing through here, okay, through this branch. Using voltage probe, then we must compute the supplied current. Okay, this is IP. And then at this node, this is branching. So KCL at V1 here, V1 negative VP, V1 negative 0 divided by 1K plus V1 negative 2Vx here divided by 2K plus V1 negative 5 VP divided by 1K equals to 0. Then the controlling variable Vx equals to Vp here negative V1 divided by no Vp negative V1. Yeah? So that's like the potential difference between these two nodes. Then solving the equation, so putting this equation into this part, then we will to replace Vx, then we will obtain the relationship between V1 and Vp, or alternatively, if we replace V1 here with Vx, V1 equals Vp negative Vx, we will obtain this relationship. Okay, then Ip that is equals to the current here, Vp divided by 2K here, to I3, yeah, I3, plus Vp, this is KCL at this node, yeah, Vp negative 2Vx divided by 1K, plus Vp negative V1, which is Vx, divided by 1K. So then from here, after if we put the value Vx here, we replace with this value, okay, then we will obtain Ip equals to 15 Vp divided by 14K. So if we have Vp 1 volt, okay, so Ip equals to this one, yeah, 14 divided by 15 kilo ohm. Okay, because RTH is Vp divided by this one, so 14 divided 15 kilo ohm. So when we have only dependent sources, so what we need to find is only then the Thevenin equivalent resistance, and no need to, because the voltage Thevenin source is short circuited. Okay, another example. Find the Thevenin equivalent circuit of the circuit here between A and B, and it contains only dependent sources. So V Thevenin equals to 0. To compute the equivalent resistance, we apply an external probe. Let's try to use the current probe here, like this, 1 milliampere. Okay. So the Thevenin resistance will be Vp, yeah, across this independent probe, this current probe divided by the current Ip. Then we can analyze this using conventional circuit analysis with dependent sources, yeah, using node analysis. We can also use loop analysis if we want, actually. So at V1 here, so V1 negative 2000 Ix divided by 2K plus V1 divided minus 0 divided by 1K plus V1 negative V2 divided by 3K equals to 0. At V2 negative V1 divided by 3K plus V2 negative 0 divided by 2K, then equals to this Ip, which is 1 milliampere. In this case, we apply 1 milliampere current source. So the controlling variable here, Ix, is the current flowing through this 1 kilo ohm equals to V1 divided by 1K. Okay. So from here, then we simplify further. We obtain from these two equations 3 V1 minus 2 VV plus 6 V1 plus 2 V1 minus V2 equals 0. Yeah, then from here, Ix we substitute into this value, and then we obtain this one, 2 V2 minus V1 plus 3 V2 equals to 6 volt. Yeah, this one from this equation, the second equation. Then from here we simplify it further into 5 V1 minus 2 V2 equals 0, and negative 2 V1 here plus V2 equals to 6. So from here, this part is multiplied by 2, this part is multiplied by 5. Yeah, from here, then we obtain V2. Yeah, the voltage across this 2 kilo ohm resistor, 30 divided by 21, or 10 over 7 volt. Okay, then Vp, which is equals to V2, right? And IP is 1 milliampere. So RTH here, so VP is basically this one, yeah, equals to V2. RTH is this voltage divided by 1 milliampere. So we obtain 10/7 kilo ohm. So the resulting equivalent circuit is this one with RTH equal to 10/7 kilo ohm. Okay, I think that we all for today. So these are just sample problem, which is basically similar to the previous example. So in this case, yeah, you just, if you are confused with this, you just need to redraw it. This one similar if you are asked to replace the whole thing using Thevenin equivalent, you can replace using 1 milliampere source. So if you are confused with this drawing, you may redraw it such that the AB will be on the right part. Yeah. Okay, so the next week we will continue with circuit having both dependent and independent